Welcome to the RF Integrated Circuits course, which is EE6240. So before we start with the theory, I'll tell you what textbooks are going to be used for the course, some reference textbooks. I'll cover the course format, and then I'll talk about the prerequisites. Then I'll quickly tell you what topics will be covered in this course. So first, the textbooks. So we'll primarily rely on two textbooks. The first one is called RF Microelectronics. This is very useful for systems and radio architectures. So this book is written by a professor called Behzad Razavi from UCLA and is published by Prentice Hall. The second important book we'll use is called The Design of CMOS Radio Frequency Integrated Circuits. And this is very useful for the circuits portion of the course. So he gives a lot of detail on RF integrated circuits. This book is written by Professor Thomas Lee. From Stanford, and is published by Cambridge University Press. Another useful reference is called VLSI for wireless communication by Professor Bosco Leon. This is also published by Prentice Hall. So we'll primarily use the first two textbooks, but this one is useful because it bridges the gap between systems and circuits. As far as the course format is concerned, you should remember that this is an advanced level MTech course, so what that means is you should be prepared to do a lot of work outside class through projects and assignments. So we will have 4 mini projects in this course, which will account for 40% of the grade. We'll have one final exam, which will account for 30% of the grade. We'll have a journal paper seminar, which will account for 20% of the grade, and probably 5 to 6 homeworks, which will account for 10% of the grade. And what we'll do is, as far as submission goes, we'll do it through email. The prerequisites for this class are EE5390, which is analog IC design, or if you have a similar background, that is satisfactory too. Should have a good understanding of MOSFET operation. So some basic MOSFET devices and the small signal model of the MOSFET. You should also have an understanding of basic signals and systems, so what I mean is you should be comfortable with Fourier series, Fourier transforms, etc. And you should be comfortable with thinking in the frequency domain. And obviously the time domain too. So the topics we'll cover in this course are we'll cover the RF basics, and then we'll also give a brief introduction to analog and digital modulation schemes. Then we'll cover S parameters, resonance and impedance matching. After that we'll look at what kind of inductors, capacitors and other passive circuits are available for use with integrated RF circuits. We'll have a quick introduction to short channel MOSFET operation, and behavior. Next, we'll study noise and distortion. You'll see that noise you might have already studied in the analog ICs course, but distortion, the way distortion is quantified in RF circuits is slightly different from that in other analog circuits. Then we'll look at receiver architectures. What we'll do is, at first we'll try to briefly touch upon receiver architectures so that we can start looking at some of the circuits that are involved in receivers and transmitters. Then later we'll study transmitters and receivers in a little bit more detail. So after that, we'll look at RF circuits. So we'll look at low noise amplifiers, mixers, voltage controlled oscillators, and if you have time we'll also try to look at power amplifiers. So we'll primarily look at design and operation of these circuits. Then we'll come back of course to RX and TX architectures. Then we'll probably have maybe one class of introduction to RF layout. So now that we have some understanding of what we are going to study in this course, let's start off with the first lecture. So what do you understand by radio frequency? So the modern understanding is, people tend to think of, let's say, very high frequencies, right? Transmission, reception, and so on. And in reality, you can define RF as any frequency, or rather the frequency of any signal that carries information. It can be wired or wireless. But you'll see nowadays the majority of RF work happens in the wireless domain. Some examples are cellular phones, wireless LAN, television systems, AM and FM radios, and so on, right? There are hundreds of examples. If you look at modern systems, so you have three major portions. So you have the digital portion, you have the mixed signal portion, and you have the RF portion. And the RF portion directly interfaces with the antenna. So if you see the way data flows in this system, the digital system interfaces with the analog system, with the mixed signal or analog system. The mixed signal system interfaces with the RF system, and the RF system interfaces with the antenna. So this is the flow of data. But if you look at most of these integrated circuits, what you'll find is you also see interface in the form of control. So you have several means of control exercised by the digital system over the mixed signal and RF domains. What happens in the digital system? So you have what is called baseband processing. So typically this could be the processor, it could include the modem, etc. The mixed signal portion includes the ADC, the analog to digital converter, the digital to analog converter, etc. You have a bunch of other systems. So you have the audio amplifier and so on. The RF system usually contains low noise amplifiers, mixers, and nowadays the PAs and so on. So there are lots of components. So what we study in this course, we'll study transmitter architectures, transceiver architectures, and we'll study the circuits. This usually comes under the RF systems domain, because you need to understand the interaction between the RF and the baseband. And RF ICs, of course, includes design, which is circuit design, and typically you'll look at, as part of this, you'll look at new circuit topologies. Now, what makes RF so interesting? What you'll find is RF is very multidisciplinary. Okay, what does that mean? So if you look at RF design, there are a number of ingredients which go into RF design. So you need to understand the theory of signal propagation. You need to understand IC design. So you need to understand CAD tools. You need to understand a little bit of COM theory. You need to know a bit about wireless standards. You need to know your microwave theory well. And you need to have a good understanding of TX and RX architectures. Okay, to lesser or greater extents, you need to know all of these. Now, what we'll study in this course, we'll study this in detail, and we'll try to study this in as much detail as possible. And the other thing to keep in mind is you folks will be using CAD tools for your simulations and design. The thing to remember is CAD tools are indispensable. For modern RFIC design. However, do not over rely on CAD tools completely. Keep in mind your intuition and knowledge. We'll also look at what Professor Razavi calls the RF Design Hexagon, which describes the trade-offs in RF design very well. So what are the different parameters that you would trade off? You have noise, you have power, you have frequency, gain, your supply voltage, let's call it VDD, but all of these are two-way arrows. Then you have linearity. So you have a design hexagon. So each one of these can be traded off with one or more of the others in a specific way. So the next thing you'll find is, in this course, most of the work we do will be in CMOS. Why? So the traditional reason is, in the case of digital circuits, so you have several advantages. Require very few devices per gate. So that makes it very attractive as far as density goes. Then you have no static power dissipation. Then the MOS devices can be easily scaled down to achieve higher and higher densities. Okay, and coupled with this, you also have what are lower fabrication costs compared to bipolar processes, especially in the presence of high volumes. Now, why would you want to use it for analog or RF for that matter? So, of course, the number one reason is you have the possibility of what is called a system on chip. Okay. So what that means is you can have a single chip with digital, mixed signal, RF. Okay, all three functionalities. And that means the lesser number of interfaces with the external world, which is always better for us, as well as cheaper. You can sell the whole chip at a much cheaper price. But what you'll find is, as you delve deeper, you'll find that there are certain issues nowadays. Before you go there, let's look at one more advantage of CMOS for analog, which is they've become comparable to BJTs in FT, which is speed, and this is a little bit more controversial, but it's in some cases their noise performance is better. We'll just put a question mark there just to see. It'll require a little bit more investigation. So if you see 20 years ago, CMOS was considered to be very slow, very noisy, but nowadays the first choice of anybody who's going to design analog ICs is CMOS. What are the issues with CMOS? No longer cheap. So now what has happened is the number of masks has blown up, which means a larger cost. Lithography is getting very expensive because you need to go to better and better, rather more and more resolution for the lithography, so it's getting extremely expensive. And the next problem is leakage current. With your current nanometer level CMOS circuits, CMOS transistors, you have a large leakage current, which means static power consumption. So you have to be very careful with your design. If you look at, I believe in the mid 60s, Gordon Moore at Intel came up with what is now known as Moore's law. What is that? He claimed that the number of transistors, actually his claim was slightly different. He said the number of components, but the number of transistors is also acceptable. Number of transistors on an IC doubles every 2 years. Now you'll also see multiple numbers for this 2 years, because some people say it used to be 1 year, then it was 2 years, some people will say 18 months. So the exact time does not matter. What matters is there is some kind of linear relationship as time in terms of if you look at the number of transistors versus time. and if you see more or less, so if you see we have gone somewhere around this linear kind of scale, but we more or less lie on this axis, on this line. Okay, now that we have had a quick look at why we are using CMOS and what RF is, let's look at what we need to know a little bit, some other things we need to know about RF. So let's first look at path loss. So let's say you have, so just remember this is the standard notation for an antenna. So let's say you have a transmitter and it is transmitting a signal to a receiver which is at a distance d from the transmitter. What you'll find out is the signal power loss can be shown to be proportional to d squared in theory. Well and good. Now what happens if you have a reflective surface that causes multiple paths, let's say a second path. So let's say you have a reflective surface. So this is your direct transmission and this is your a second transmission path, reflective path. What you can find is that the power loss is empirically proportional to the fourth power of the distance. Now in real life you can have multiple reflections. You could have moving obstacles, which means time dependent reflections, and which means time dependent power loss. The phase of the signal path matters. In other words, you could have constructive or destructive interference. So depending on all of these things, you could get a certain power profile at the receiver. So what you'll find, so if you take into account all of these, you get a phenomenon called multipath fading. So if you look at your log of your power loss versus the distance, what you'll find is you have a certain ideal slope of 4, but your real signal could do something like this, right? This is your actual loss. So it's just the slope of 4 is an empirical quantity. Okay, so now next let's look at what is meant by diversity. What do you understand by diversity? It refers to some kind of redundancy. So usually in the transmitter or receiver. Actually, in the transmitter or receiver paths. So you have different kinds of diversity. So if you see, you have what is called spatial diversity or antenna diversity. What does this mean? All this means is you have two or more antennas, and you can choose to operate either. If you have two antennas, you can choose to operate either one of the antennas, so that your probability of having fading at both antennas at the same time is very little. Usually you would have some multiple of lambda by 2 spacing between the antennas. The reason is, if you have completely destructive interference at one of the antennas, that means that at the other antenna you would have close to constructive interference. Now the other kind of diversity is frequency diversity. What does this mean? This means two or more frequency carriers. So you could either transmit and receive at multiple frequencies. So that is one option. The other option is, now this may technically not come under frequency diversity, but you could also do what is called frequency hopping. That is, at every transmission you could change your transmission and receive frequencies, so that the probability of having fading at both frequencies will be very little. And the last kind of diversity we'll look at is time diversity. What is meant by time diversity? Time diversity refers to, so you send the data more than once. Mainly to overcome short-term fading effects. For example, you could have a, let's say, an object, a moving object, maybe a car, maybe a person walking through a room. It could be a number of things which could cause short-term fading. So if you send the data once more, you are sure to receive it the second or third time. So that is time diversity. So we'll stop here for today's class and continue on Wednesday.